So I first of all thank the organizers for giving me this chance to present some of the work that I have done with my student Sri Lakshmi and my collaborators Professor Lakshmi Bala and Professor Balakrishnan at IIT Madras. Um, so the rough outline is as follows. I will begin describing the motivation to look at two-particle entanglement for atomic as well as nuclear system. In preliminary studies, which was carried out with the coupled oscillator model, proved to be an extremely useful exercise as it gave us analytical results with which we could check our codes, as well as gave some insights into what needs to be done when we move on to problems involving the deuteron or the hydrogen atom, which are actually in 3 dimensions. So in this coupled oscillator problem is, of course, in 1 dimension. And so I'll talk about the coupled oscillator, and then mention the results that we have with the hydrogen in the hydrogen atom as well as in the deuteron problem, where we study particle entanglement. And finally, if time permits, talk about the deuteron on a quantum computer. So the entire idea of looking at entanglement between between particles arose in the context of strongly correlated system. We wanted to understand if there was any connection between particle entanglement and binding, and again once more, if there was any connection between entanglement and what you see in many particle system, which is correlations between them, as well as we wanted to look at simplifications that one can have in many particle systems. For example, when you perform many particle computation, if the system is strongly correlated, then the resource requirement is quite large. Therefore, traditionally in many body computation, one looks at possible ways of minimizing these correlations or taking these correlations into account in a simplified fashion, which could mean resummations, it could mean some alternate ways of getting interactions and so on and so forth, so as to minimize correlations so that you can carry out these computations more efficiently. So we wanted to see if there were signatures in entanglement with respect to these aspects. Now, entanglement is something that everybody has seen, perhaps in a second course in quantum mechanics. For example, if you have 2 spin-half particles, you know that the Hilbert space is going to be 4-dimensional. You could have up, up, down, down, up, down, and down, up. But instead of working in this basis, one can also construct the coupled basis, where you talk in terms of the total spin. So if I add 2 spin halves, the total spin can be 1 or 0. And the corresponding projections, if spin is 0, if the total spin is 0, is of course 0. And if the total spin is 1, the projections can be 1, 0, and minus 1. So accordingly, if you take this coupled basis and write out the uncoupled basis, then you know that a state which is total spin up and projection up can only be given by the up spin in the uncoupled basis. Similarly, if I have total spin up, total spin 1 and projection minus 1, it can be only written in terms of the down state. And if I have total spin s equal to 1 and projection 0, then I can have 2 combinations, which is up plus minus down up. Now it turns out if I have the total spin s to be 1, it is the symmetric combination, which is up down plus down up, that contributes. And when the projection, where the total spin is 0 and the projection is 0, it is the antisymmetric counterpart that contributes. This, of course, the total spin s equal to 1 is the triplet and s equal to 0 is the singlet. But what's important to note is that the triplet has entangled as well as separable states. So the states corresponding to s equal to 1, ms equals plus 1 or minus 1 can be written as completely separable states in terms of the uncoupled spin. Whereas if I have s equal to 1 or 0, but the spin projection is 0, it is always written in terms of the entangled state, which is up, down, plus, minus, down, up by root 2, which is what you have here. And this is a simple exercise that would have been done in a second course when you deal with Clebsch-Gordan coefficients and so on, and the coupled and the uncoupled phases. Similarly, in strong interactions, in addition to spin, you have the isospin degree of freedom, where the proton and the neutron is considered as as a doublet, which under isospin, and you have the math is very similar, and again you have this entangled state, which is NP plus minus Pn by root 2. So these are simple examples of entangled states that we see early on in perhaps an advanced undergrad or a master's course. The other system, which we are all very, very familiar with, is the hydrogen atom. So this is a two-body system, and the most efficient way of solving this two-body system is to change variables to center of mass and relative coordinates, and so that the total wave function here given by psi of little r comma capital R, where little r is a relative coordinate, which is defined here, and capital R is the center of mass coordinate. M1, M2 are the masses of the two particles, R1, R2 are the position vectors of the two particles, and capital M is the sum, is a total mass, which is M1 plus M2. You see that in this, once you change coordinates to relative and center of mass, the hydrogen atom wave function becomes separable into a part that depends only on the center of mass and a part that depends on the a part that depends on the radial coordinate. Of course, the interaction depends only on R in the hydrogen atom with the central force problem, and therefore the center of mass completely separates out, and the solutions are in terms of the plane waves, which of course has box normalization. The dynamics and the interesting part is, of course, in the relative coordinates, which is then solved, and you have the familiar hydrogen atom wave function. Now, if you don't look at it in terms of the center of mass and the relative coordinates, but instead look at it in terms of the single particle coordinates R1 and R2, then so the wave function is not separable, and therefore one can ask, how does one understand entanglement in this problem? For example, you can ask, how does one, if I integrate out the proton, how does one understand electron entanglement in this problem? So in order to understand the important ingredients that, because these are all continuous variable systems, so the Hilbert space is infinite dimensional, and for the moment I'm going to forget about spin. I'm only going to look at space entanglement between particle 1 and particle 2. A very useful model is to look at the coupled oscillator model, which is a 1D problem. You have oscillator 1 and oscillator 2 given by the suffixes 1 and 2. And this term here, which is m lambda x1, x2, is the coupling between the two 1D oscillators. Lambda is the coupling parameter, m is the mass, and omega is the frequency. Just to get notation straight, given a pure state, the density operator rho is defined by the outer product. So for example, going back to the familiar spin half system, and I have two spin half, you know that the uncoupled basis is going to be just the collection of these spins, up, 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 down, down, up, and down, down. It is possible, as I said, to write the coupled basis in terms of the uncoupled basis. So now, as an exercise, one can define, so this 1, 0, for example, is a pure state. I can form the outer product and write the density operator for this state 1, 0. Now, it is, if I can trace out the second particle, then I get the reduced density matrix. Similarly, I could also have traced out the first particle, and I'll get the reduced density matrix for the second particle. Now, this reduced density matrix has the following property, that if I find its trace, it is 1. However, starting with this state 1, 0, the trace of the square of the reduced density matrix is less than 1, and that is because you're starting with an entangled state. On the other hand, if you had started with the 1, 1 state, which is completely given as just the up spin, then this is an unentangled state, and therefore if you find the reduced density matrix, both its trace of the trace of the reduced density matrix as well as trace of the square of the reduced density matrix would be 1, because it's an unentangled state. So therefore, this fact that the trace of the reduced density matrix is less than 1, it tells you that it's a mixed state. And one can define entanglement measures, which is the subsystem linear entropy, which is 1 minus trace reduced density matrix square, and the subsystem von Neumann entropy, which is defined here as minus trace rho log rho, where rho is a reduced density matrix. So this is just to get the notations clear. So now, with the two particle wave function, it could be the coupled oscillator, it could be the hydrogen atom, it could be the deuteron. I define the density matrix in the position space. Then I can find the reduced density matrix and the square of the reduced density matrix. Now you see, if it is a 3-dimensional problem, then you need to integrate over, you have to do a 3-dimensional integration over one of the variables. And it gets much more complicated when you have to find the square, because each of these involve an integration over 3-dimensional space. So totally you have a 9-dimensional integral, which you can simplify by choosing axes and so on. But still, in order to do this, one has to use something like a Monte Carlo algorithm to carry out this integration. So it is very indeed numerically hard to calculate the reduced density matrix as well as its square, and then you have to compute its trace. So in order to understand all the details, for example, one important thing that came out is the fact that unless the center of mass is localized, the reduced density matrix vanishes. Therefore, the SLE and SVNE diverges. So SLE always becomes 1, SVNE always it goes to infinity, and therefore there was this result that one needs to localize this center of mass. And this is where I would like to emphasize that usually when you do a hydrogen atom problem, one does not pay much attention to the fact that you're box normalizing, you have a plane wave and it's box normalized, and that the solution is not localized. But this becomes extremely important in this context, that you cannot use a plane wave solution here because the omega continues to stay. And when you take the limit omega going to infinity, which is sort of done very quickly when we are dealing with just the the eigenvalue equation for the hydrogen atom, we don't even think of the center of mass, but one has to worry about this, and in fact one has to localize the center of mass in order to see, in order to demonstrate this without being bogged down by these higher dimensional integrations. We looked at the 1D coupled oscillator model. Very similar to the hydrogen atom or the deuteron. If you switch to the center of mass and relative coordinates, the two oscillators completely become uncoupled, where one can define the new frequencies omega c and omega r, which are the frequencies of the center of mass oscillator and the relative oscillator in terms of the original frequency omega. I should mention that this is an isotropic oscillator with a coupling constant lambda. You can define it in terms of this. Now, if I set lambda equal to 0, it is very easy to see that the center of mass and the relative oscillator frequencies become one and the same, and you have the uncoupled case. So therefore, the Hamiltonian becomes uncoupled both in the single particle basis as well as in the coupled basis. And the number operator, which can be defined as AR dagger AR plus A capital R dagger A capital R, is as well as A1 dagger A1 plus A2 dagger A2. It becomes the constant of motion in both the single particle basis as well as in the coupled basis. Now, what I want to do is the simple exercise of writing out the coupled basis in terms of the single particle basis. This is what you did with the spins. If I choose a particular value of NC and NR, then it's conceivable that this can be written as a linear combination of the uncoupled bases N1 and N2. However, if I choose NC equal NR equal 0, then there is only one unique choice for N1 and N2, which is N1 equals N2 equals 0, because total N is conserved. And as a result, you get a separable state in both the bases. However, any other choice of NC and NR, for example, I could keep NC equal 0 but have non-zero value of NR, or the other way around, I will always have states which are entangled with respect to the uncoupled states. So this has direct analogy with the spin half addition, except that this is no longer spin half, but you have these oscillators, therefore you have two infinite dimensional Hilbert space which are coupling together. So for the uncoupled case, if I keep NC equal 0, it is possible to solve this analytically. Both SLE and SVNE have exact solutions, closed form solutions given here. And holding NC equal to 0, if you change NR, you see that both SLE and SVNE grows. The blue is the SLE and orange is the SVNE. You're able to see my cursor, correct?
Yes, yes.
Yeah. So the first thing that we understand from this is that NC equal to 0 implies that the center of mass oscillator is in the ground state, and the relative oscillator, as I increase NR, goes to higher excited states where the binding energy increases. So when the binding increases, of course, you only have bound states here. It's an oscillator problem. You see that both the entanglement measures increase. Therefore, there seems to be some correlation between increase in binding and the growth of these measures. Now, if I keep the coupling, so when lambda is not equal to 0, it means that the oscillators in the single particle basis are coupled, but in the coupled basis, which is the center of mass and relative, it's of course uncoupled. In the case where NC and NR is 0, therefore both the relative and the center of mass oscillators are in the ground state, it is again possible to get closed form solutions. And here is a plot of SLE and SVNE as a function of eta, which is the ratio of omega C over omega R. Now, before we go to the plots, first of all, you see from these expressions that there is a symmetry if I take, under the transformation, eta going to 1 over eta. And this is, of course, reflected in both these plots. And in addition, you see, when eta becomes very large, for both SLE and SVNE, which equals to omega C becoming very large, or omega R are becoming small, the SLE as well as SVNE diverges. And the same situation happens at the other end when eta becomes very small because of this symmetry. All right. So therefore, both SLE and SVNE diverges or does not have any sensitivity to the state, or it's characterized by a set of quantum numbers if you do not localize both the center of mass and the relative oscillators. Now, in the case of hydrogen atom, or in the case of deuteron, the relative solution is always localized, but the center of mass is not. But the take-home lesson is that one has to work with a localized center of mass. This, then, of course, we could numerically calculate for the lambda not equal to 0, but NR not equal to 0. So the analytic solution was when NR was also equal to 0, but in general, when NR is not equal to 0, you see the same features, which is as a function of eta, you need to localize the center of mass oscillator, as well as, of course, the relative oscillator, because these are two coupled oscillators. Then you get sensible results. And you see that as NR increases, this means if I choose a reasonable value of eta, then you see that as NR increases, the entanglement measures also increase along with the binding. So if I have to calculate SLE and SVNE, as I told a couple of slides ago, you know that it is going to become numerically expensive as one goes to three-dimensional systems. Now, instead, it is possible to look at distance between probability density distribution, which is the Kullback-Leibler and Bhattacharya distance, which is something that you have learned, you have heard about, you've heard of in the other two talks. It is possible to define distances using Kullback-Leibler and Bhattacharya distance. So with the probability, with the wave functions, it is possible to find the PDF of both the combined wave function of two particles. So x and y represent the two particles. So in this case, x and y, for the oscillator case, would represent oscillator 1 and oscillator 2. The denominator, the tildes, the row tildes, are the reduced density matrix where you've integrated over one of the oscillators, 1 or 2. Then you have here the definition for the Kullback-Leibler and the Bhattacharya distance. Now, it is in the previous literature, it has already been shown that these distances capture quantum entanglement, and they have been used in the context of optical tomograms. Just to recap and connect, where you define the optical tomogram as the diagonal matrix element of the density matrix, and for different values of theta, you have different quadratures. Here, of course, with this oscillator problem, you could either work in position space or Fourier transform the wave function to the momentum space. So you just have two quadratures, which corresponds in the quadrature parlance to theta equal to 0 and theta equals pi by 2 respectively. Because you can see that if I put theta equal to 0, x theta would correspond to x, and if I put theta equal to pi by 2, it corresponds to the momentum. Okay, so that is just to make a connection with what is done in quantum tomography. So we looked at Bhattacharya distance as a function of eta. This is the x slice and p slice, but taking an average between them, we get back the symmetric result that you saw for SLE and SBNE. And again, we have the coupled, the NC oscillator, the center of mass oscillator, to be in the ground state. And as I increase the NR quantum number, the binding energy increases, and so does this entanglement measure. Here it is the epsilon BD, which is the Bhattacharya distance. The same story holds for the Kullback-Leibler divergence. So therefore, the take home, just to summarize what we have seen in the coupled oscillator case, is that first of all, if the center of mass is not localized, both SLE, SVNE, the same holds for Bhattacharya distance, Kullback-Leibler divergence, all of them diverge, and therefore it is imperative that the center of mass is localized in a trap. Further, as the binding energy increases, all these entanglement indicators increase in value. So this sets the stage for similar computation for two-body systems. I'll look at the hydrogen atom first before we look at the deuteron. So for the localized hydrogen atom, you have the center of, this is the relative eigenvalue, the value problem that you solve and get the phi NLM, which has a radial part given in terms of the associated Laguerre polynomial, as well as the spherical harmonics for the angular part. And what is left, instead of the familiar e to the I p dot r, you have the oscillator, the center of mass to be in the ground state of an oscillator. So you're localizing the center of mass. Again, once more the notations. Little r refers to the difference between is the relative coordinates, which is Re minus Rp, and capital R is the center of mass of the two particles, which is the electron and the proton. So then again, what I want to do is, given this psi, I want to build a density matrix and get the reduced density matrix by tracing over one of the particles. Of course, I choose to trace over the proton because I'm interested in the entanglement of the electron. Now, if I calculate SLE and SVNE numerically and do it as a function of n, which is the principal quantum number, keeping L and M to be 0, then we see that as n increases, the binding of the electron to the nucleus decreases, and so does the entanglement. And the same story holds. Of course, sorry, this is SLE, not and this one is not SPNE, but it is the Bhattacharya distance. The same story holds with the Bhattacharya distance as well. As you see that both Bhattacharya distance as well, it keeps track of the entanglement like the SLE and the SPNE. So therefore, we see that once you localize the hydrogen atom, you see that there is a direct correlation between the degree of binding and entanglement. This sets the stage for us to look at the two-body problem in the nuclear case. So here the only two-body, so here you have a neutron and a proton. You could have two protons or two neutrons. However, the only bound state that is formed is that between a neutron and a proton. This bound state is the deuteron. But the nuclear interaction is much more complicated compared to the central potential problem that you have seen in the hydrogen atom. To begin with, it depends on spin, it depends on space, it depends on isospin, and the interaction itself is non-central. There is a coupling between the spin and space, which is called the tensor force, and that results in the interaction not being a central interaction. Therefore, there is no, the interaction changes as one changes the total spin, the isospin, and so on, and the total orbital angular momentum. As one changes it, the two nucleons will see a completely different interaction. Because of the internucleon interaction being non-central, there are some quantities which are conserved and some quantities which are not. It is known that the total spin is conserved, the total isospin and its Z component is conserved, and however, L, which is the orbital angular momentum, is not conserved. This happens because of the non-central nature of the interaction. As a result, the Hamiltonian will be diagonal in spin, isospin, the Z component of isospin, but not with respect to L. So therefore, instead of one can get one more, a good quantum number by coupling spin and orbital angular momentum, namely the total orbital angular momentum. The Hamiltonian indeed commutes with J square as well as Jz. So therefore, for good quantum numbers, you have J, Jz, S, T for isospin, and Tz, which is its Z component. In addition, the interaction conserves parity. And therefore, usually, because I said the interaction is a very complicated interaction and it's different depending on what values these quantum number takes, it is usual to use the spectroscopic notation to talk about these interaction in terms of the quantum numbers. For example, if I look at this 1s0, the superscript refers to the value of J. It refers to the spin multiplicity. The S symbol refers to the L value and the subscript refers to the value of J. So S implies L equal to 0. The spin multiplicity 1, which is seen in the superscript, refers to S equal to 0. So therefore, it's not a surprise that J, which is the subscript, is 0 because L is 0 and S is 0. Now, if I change the value of spin to 1, because if I have two spins, two spin half particles, which is the value of spin for neutron and proton, the total spin can be 1 or 0. So we saw the case when the total spin was 0. So now if the total spin is 1, then the spin multiplicity becomes 3, which is given by the 3 here in the superscript. The L is still 0, so you have S, but the J value, which is the sum of L and S, is 1, which is given by the subscript. Then you can ask what happens if I change the value of L. Then you have S equal to 0, S equal to 1. So that gives you the 1p1, 3p0. But because L is 1, you can have more values for J, which is 0, 1, and 2. And therefore, you have 0, 1, and 2 given in the subscripts for the p waves, which is 3p0, 3p1, 3p2. Now, you see that I seem to have highlighted the 3s1 and 3d1 together in red, and 3p2 and 3f2 together in red. These two, this highlighting is due to the fact that the L value is not conserved. However, S, J, and T are conserved. Therefore, it turns out that 3s1 and 3d1 can have an overlap through the Hamiltonian, because this corresponds to L equal to 0, this corresponds to L equal to 2, so parity is conserved. In both cases, total spin is 1, so spin is conserved. In both the cases, S is 1, J is 1, so total angular momentum is conserved, and it also conserves T, which is the isospin, since L is 0 and S is 1. Isospin has to be 0, so that you satisfy the generalized Pauli's principle, that is spin, space, and isospin should result in an antisymmetric wave function. So the same story holds for the 3p2 channel, that it is coupled to the 3f2 channel. Now, the fact that you have this non-central interaction was known experimentally because the deuteron, when it was discovered, was found to be a very shallow bound state. The depth of the nuclear potential is about is of order of hundreds of MeV, whereas the deuteron binding energy is about 2 MeV, and the range of the nuclear interaction is few Fermi, whereas the deuteron's size is of order is bigger than the range. It's about 2 or 3 Fermi. And in addition, it was found, the spin of the deuteron was found to be 1. The total orbital angular momentum was, angular momentum was 1, the J was 1, isospin was 0, and it had this curious quadrupole moment, which immediately signaled the departure from spherical symmetry. So it was experimentally known that the deuteron was not spherically symmetric, and hence it was possible to build an interaction where there was a term which had to break the spherical symmetry, which was the tensor interaction. So historically, one understands the nuclear interaction as something like a molecular interaction. So here is a schematic where you have short range attraction, intermediate and short range repulsion, and intermediate and long range attraction. The long range part is mediated by 1 pion exchange. The short and intermediate are mediated. You can model it differently. You could think of it as heavy meson exchanges, or just you can put in any favorite model of your choice. As long as the 1 pion exchange term is there, you fit the parameters of the model to reproduce experimental data, and lo and behold, you have a two-body interaction. So all of this is to tell you how much more complicated the nuclear problem is compared to the simple atomic problem. Now, therefore, if I have to write the two-body wave function for the deuteron, it is going to be extremely complicated. So here is the two-body wave function for the deuteron with the corresponding quantum numbers fixed, where J is 1, T is isospin is 0, and spin is 1. And this is, of course, in momentum space, because it's easier to work with momentum space, where you diagonalize the Hamiltonian given an interaction, and you solve the eigenvalue problem numerically. Then you see that if I write it in terms of the single particle quantum numbers, I have to express it in terms of the coupled quantum numbers, because I know the wave function only in the coupled basis. The C's here are the Clebsch-Gordon coefficients, which you must have seen in an earlier course with spin, isospin, and this, of course, is the coupling between L and S to total J. This is again you have to it's complicated numerically by the fact that you have to localize the Gaussian. So it's a very numerically challenging problem to find the density matrix, the reduced density matrix, as well as SLE or SVNE. So instead of working with SLE and SVNE, since I have now convinced you that one can look at the diagonal matrix element and look at the Kullback-Leibler or the Bhattacharya distance without any further fuss, I'm going to look at the Bhattacharya distance as a function of the width of the Gaussian wave function that tells me, that localizes the center of mass. You see something similar. So if you remember, for the oscillator, we had the entanglement indicator as a function of some parameter which tells you how localized the center of mass is. And this again, the BK plays the same role. You see the same thing, that if you do not localize the center of mass, the indicator is going to diverge. Otherwise, it gives you something sensible. The two curves correspond to two different values for the Jz, which is Mj equals 0 and Mj equals 1. Since it's only one bound state, there is nothing more you can do with it. So you just have a number. You have to now look at other parameters that one can vary, which I will come to in the end. Now, the coming back to the nuclear many-body problem, this problem has sort of been around for over a century, because it still does not have an ab initio theoretical description. And it's partly because of the complications that occur at the two-body level, as well as also because of the fact that its nuclei are composite objects. So you have QCD on one hand, which is the correct theory of strong interaction. However, you want to talk in terms of neutrons and protons when you look at properties of nuclei, because QCD is useless for the energy range where nuclei live, which is of the order of few kiloelectron volts to MeVs. Okay, whereas so then what we know about nuclei is given in by this chart, which is the table of nuclei. Here you have the number of neutrons along the x-axis and the number of protons along the y-axis. The black squares here refer to the stable nuclei. And if you observe, without even from just simple undergraduate physics, you see that you have equal number of neutrons and protons all the way till, say, calcium 20. You have 20 neutrons and 20 protons for a stable isotope, after which stable isotopes favor more neutrons compared to protons. This is a very this is a common sense explanation to it, because you want to bind neutrons and protons in a volume of order of whose radius is of order of few Fermis, which is 10 to the minus 15 meters, and therefore one wants to minimize Coulomb repulsion. So therefore nature automatically favors more neutron-rich matter in order for them to be stable. Now, a lot of this, if I fix the number of protons and move horizontally, I get different isotopes. On the other hand, if I fix the number of neutrons and go vertically, I get the different isotopes. So now you see that much of the chart is empty. And that is because very little is known about the limits of binding. If I fix the number of protons and move horizontally, it is not clear at which number, for a given number of protons, at which number of neutron I can no longer find bound particles. That's called the drip line. So the exact location of these drip lines, both the neutron drip lines and the proton drip lines, is not known. And you see that there are many processes which happen here in the unstable, in the region where you have unstable isotopes, and these processes happen in the stars. And what is interesting is that many parts of the chart are not even experimentally accessible. Now, and these objects, because of their substructure and the fact that you have interactions which are very complicated, for a long time it was not possible to calculate beyond carbon-12 using state-of-the-art ab initio calculations. It was a typical shell model calculation, for example, for a nucleon which has 50 nucleons, a nuclei which has 50 nucleons. It requires 10 to the 7 to 10 to the 9 states. So really these calculations, the computational requirement becomes demands become very large, very heavy, and therefore ab initio calculation for neutron-rich nuclei matter becomes infeasible. But not to worry, there are different many-body methods which would allow one to go through the chart. But because there is no ab initio connection, each of these methods will become intractable because there is a lot of model dependence that come in. Now, in order to understand why this model dependence comes in, in order to understand why this model dependence comes in, it is nice to just look at just the two-body case. If you recall, I told you that it looks very much like the interaction looks very much like the molecular potential, where you have short-range repulsion and intermediate and long-range attraction. And I also mentioned that it's usual to do this calculation in momentum space, because in momentum space you can deal with just matrix diagonalization numerically, whereas in position space you have to solve a differential equation. But no matter which space you use to solve this eigenvalue problem numerically, the fact that you have a repulsive core is going to be problematic, because in momentum space a repulsive core implies that you are going to have matrix elements for very large values of K, which you see here. So these are different, the Paris, Bonn, AV18, Idaho, and so on are different two-body interactions. And all of them have matrix elements which have support for very large values of K. Whereas for nuclei, you see K, which goes all the way to 4 or 5 or even sometimes 30 inverse Fermi, which translates into energy scales of several GeVs, where this simple-minded non-relativistic picture is no longer valid. So therefore, this is in order to, while at the two-body level, there is no problem. You have solved the problem because you have, after all, you have experiments which guide you to fix the parameters, and your two bodies problem is solved. If you now take any of these interactions and put it into a three-body system, for example, if you calculate the binding energy of Triton, then different people, different models will give different answers, because the fact that you have the model dependence will immediately come in through possible intermediate states. However, there is a way to circumvent this model dependence, and that way comes through the idea of effective field theory and renormalization group approaches. So the idea is extremely simple. Suppose I have a complicated system. So this is a snapshot of the atomic nucleus. You have the quark structure sitting inside each of these nucleons. If I probe this system with probes where the wavelength is much smaller than the size of the size of the nucleon, then it is possible to resolve the quark substructure. On the other hand, if I have long wavelength or low energy probes, then it's not possible to resolve the quark substructure, and therefore one can do with something very simple, which is replace the protons and neutrons by just these simple-minded blobs. Translating it to the interaction, one sees evidence that it does not matter which model you work with already at the two-body level, because different models come with parameters which can be fitted to experiments, and the details do not matter. One can do something better by actually simplifying our model, exploiting this fact that when details cannot be resolved, you can always use a simple-minded picture, and therefore get something universal. This is done by looking at the simple two-body scattering. So this is a schematic for the two-body scattering, where you have two particles coming in and two particles going out. It scatters one, then it can multiply scatter, which is given by this schematic for the Lippmann-Schwinger equation. So here the intermediate states allow processes which go over all momenta, whereas the states here, the states of the momentum of the incoming and the outgoing particles can be low, which is typically of order of few MeVs, few hundred MeV, but the intermediate states can go over all possible energy ranges. But your theory is valid only up to an energy of GeV, where quarks start getting resolved. So therefore, you can no longer have this non-relativistic potential description. So the idea is to use that and put a cutoff on the intermediate states, whereby you change the interaction to an effective interaction. So this is the same idea of renormalization that one sees in field theory, except that you do it at the level of the Schrödinger equation. Instead of running a coupling constant, you now have an interaction which depends on the denormalization scale, which is an arbitrary scale. It is possible to set up this entire renormalization scheme of the Schrodinger equation by unitary transformation of the Hamiltonian. You could either have a block diagonal transformation or a band diagonal transformation. These are two different ways of that is been traditionally used for this renormalization. Or you can have any kind of scheme that you want, but with the idea that you want to decouple the low and the high momentum mode. So you should not have matrix elements which couple low momentum states with the high momentum states, so that you can simply forget about the details that the high momentum states carry. So if you carry this out, it turns out it gives you effective interactions which have resulted in a lot of progress in nuclear structure calculation. In fact, over the past 20 years, people have been able to progress from carbon-12 all the way to nickel isotopes, which have an atomic number of about 50. I mean, number of nucleons, mass number of 50, not atomic number. So now, what we did was to take this deuteron problem and put it in the oscillator basis. Putting the deuteron problem in the, of course, for the deuteron problem, you can study it in momentum space. It's such a simple problem because it becomes an equivalent one-body problem. But instead, we look at it in the oscillator space because it also allows one to think of quantum computing. Because if you recall, the size of the Hilbert space requirement in order to solve any nuclei scales very quickly. Therefore, the demand on the computational resources also scales exponentially. Therefore, using quantum computer could be a very good option for problems in nuclear structure. So in order to investigate what sort of simplification these renormalized, these new renormalized group perspectives have on decreasing the resources, we decided to just do the simple-minded calculation of calculating the deuteron binding energy in the oscillator basis. So here you see the deuteron binding energy as a function of n, where n represents the maximum number of oscillator shells that we want to keep, because it's after all a basis expansion. H bar omega gives you the shape of the oscillator, and the blue line is the experimental value. The green line is with a bare interaction. The bare interaction is one of the two-body interactions you could start with. It could be the argon B18, it could be the bond potential, anything. Okay. So what you see is that as you increase n, you need large number of order 35 in order to get, or well, less than that, right? So, well, between 30 and 35 in order to get, in order for this to converge to the experimental binding value if you start with a bare interaction. So you need that many basis states in the of the harmonic oscillator for this simple two-body problem. Whereas if you use the renormalized interaction, you see that by about 5 or 6 oscillator states, you have converged to the experimental value quite nicely. So therefore, this immediately tells you that using simplified effective low momentum effective interaction, which is renormalization group based, allows you to have get away with lesser computational resources. In fact, it is something like this that allows one to have a Hartree-Fock calculation in a many-body context to be a good starting point for nuclear physics. The original interactions are so complicated that for a very long time, nuclear structure did not have the advantage that atomic structure has, which is to have Hartree-Fock as a good starting point. But it came back with these renormalization group-based effective interaction. So this is just to demonstrate how efficient, computational, resource efficient RG-based interactions are compared to the bare interaction. So what we wanted to do is to, of course, understand this in terms of qubit requirement. So since it's only a one-body problem, it was possible to write the two-body as an equivalent one-body problem, where V is the effective potential. It could be the bare potential, or it could be one of these normalized potentials. Then in order to work on a quantum computer, one needs to go from the the creation and annihilation operator to the qubit basis through the Jordan-Wigner transformation. And of course, since it's a one-body problem, you don't have to worry about antisymmetrization. So there is no, the Pauli Z operator is not there in this definition. Then, in order to carry out the eigenvalue solution, simulating this deuteron eigenvalue problem on a quantum computer, you go from a second quantized Hamiltonian to a Jordan-Wigner mapping. You have an ansatz for what could be the actual deuteron wave function. The ansatz is going to have some parameter. The ansatz that we use is called the coupled cluster ansatz, which allows for excitation from the ground, from the n equal to 0 to all the different states of the oscillator that we have included. Then you compute expectation value. It's the through the VQE algorithm, because it's the ansatz which transforms the Hamiltonian into a equivalent circuit, and you have the VQ algorithm, which gives you the expectation value for the choice of the parameters that goes into the ansatz. Then, given this expectation value, you have a classical optimizer which changes the parameters, and this loop continues until there is convergence. So, therefore, you see, for an ansatz that you have, you can write the Hamiltonian. In order to carry out this ansatz, you have this equivalent circuit, which is then carried out on a quantum computer. So here are the results. So you see, as for the deuteron, as I said, you need both the L equal to 0 and L equal to 1. So therefore, when I say n, it refers to the total number of and the total number of states which is kept here. For example, n equal to 3 implies 0, 1, and 2. So, and for each value of little n, you have L equal to 0 and L equal to 2. So therefore, n equal to 3 implies I have totally 6 qubits. N equal to 4 implies 8 qubits, 10, 12, and 14. So for 6 qubits, you see that the Baire interaction in fact gives you positive binding. As you increase the number of qubits to 14, so n equal to 7 means 14, you're not even close to a negative value for the binding. On the other hand, with the renormalized interaction, you see that it quickly converges, and in fact gives you, the simulation gives you something very close to the actual binding, which is minus 2.22, and maybe we get something as close as minus 2.17. So, in order to understand, so this was the first thing that we see, that renormalized interaction in what you saw with just a simple-minded exact diagonalization also carries over to the VQE algorithm, in a sense that you need fewer qubits if you work with renormalized interaction. In order to understand how entanglement between different modes are going to be distributed, we looked at mode entanglement, which also says something about how many basis states you need to keep for the oscillator. So here is a plot of the SLE and SVNE as a function of the coupling of the chosen mode with respect to the others. For example, if I take n equal to 0, I look at the coupling between n equal to 0, the L0 and 2, with the rest of the system. So I have totally n equal to capital N equals 7. So you see that the lowest mode is strongly entangled. The next mode is also strongly entangled to the rest. Then n equal to 2 mode with 0 and L equal to 0 and 2 is the entanglement continues. It decreases, but then it really does not fall off. On the other hand, so this is the blue curve is the SVNE for the Baire. The SLE for the Baire is given by the purple curve, and that also shows the same kind of strong entanglement between the different modes of the basis. Whereas if you take the renormalized interaction, you see that by about 3, 4, 5, the entanglement flattens, which also explains why it was possible to truncate or get converged results already with n equal to 7, which means you have about 14 qubits. So to summarize, we see that we were looking at particle entanglement between coupled oscillators and hydrogen atom, and we see that it was important to localize the oscillator, center of mass momentum. For the deuteron, we looked at the solving it both in momentum space as well as the oscillator, and whatever simplification you saw with the renormalization, with the effective interaction that has made that has resulted in so much progress in nuclear physics, you also see it on a quantum computer, in a sense that the algorithm converges better for fewer qubits. Now, there are a lot of things still left for us to explore. One should look at entanglement in the presence of medium, then look at the connection between mode and particle entanglement, as well as something that, as well as look at ensembles of deuteron and look at their non-classical effects. So this is part of the work that is still in progress in the group. I stop now and I can take questions.
Thank you.
Hello.
Thank you, Professor Ramanan. Yes, questions, please.
Good afternoon, madam. Okay. So my simple question is that suppose at time t0 there are two or more pure states, quantum states, and at a time t1 there is some kind of entanglement. And how to measure the entanglement fidelity and its limitations based on the last plot that you showed some graphs n equal to 2 to 7. So what is the measure of entanglement fidelity and its limitations?
Okay, so first of all, the graph that I showed. So first of all, you are talking about time evolution. So here there is no time evolution. I'm just looking at the ground state. Okay, so I'm just looking at the ground state and nothing more there. And what I showed you was the entanglement between, you see, because after all, I've taken the two-body problem and put it in an oscillator basis. So it's a basis expansion. So usually I need to have infinite number of states for complete convergence. However, numerically, I have to truncate this at some n value. So that was the n that I used everywhere. For example, n equal to 7. Okay, so then the basis states are 0, 1, 2, 3, 4, 5, and 6. All right, for each value of n, there are two, L equal to 0 and L equal to 2. So that is a complication that the nuclear problem has. So what I showed, maybe I will share again. What I showed was, the SV and SVNE, so the mode entanglement, which means what I do is I integrate out all the other modes. I have to form different bipartites, right? Because I'm using SLE and SVNE, I have to form different bipartites. So here, for n equal to 0, I'm looking at the lowest mode. So n equal to 0, the rest is the environment is going to be 1, 2, 3, 4, 5, 6. So I integrate over the environment and look at the SLE. So that gives me the mode entanglement between the 0 and the rest. Similarly, I take n equal to 1, which means I integrate over 0, 2, 3, 4, 5, 6. So that is my bipartite, that's my system and the environment. And I again look at SLE and SVNE. So what I'm actually showing here is the mode entanglement, which tells me how strongly entangled different modes are to the rest of the system. Okay, so this only tells you that if the modes are strongly entangled, you will need to retain all these states and perhaps more for the bare interaction. As you see here, you won't even get the binding energy. Whereas with these effective interactions, because the mode entanglement quickly dies down, all right, you see that this mode is important, this mode is important, this mode is important, but by the time you've come to 3 or 4, there is not much entanglement with the rest. Right, so these modes are not so important, and it's reflected by the convergence to the right binding value, so binding energy value.
So the limiting. Okay. Sorry? So the limitings are between 0 and 1. So when there is a 1, and we can tell that it's totally strongly entangled.
Yes. So, okay. So if you are asking why, for example, you mean this one, the value of 1. Yeah,
Yes,
absolutely.
yes, yes.
That is very important, right? So it's extremely important. You have to keep the ground state. See, because after all, you are, this also tells you how, if you expand the wave function in the oscillator basis, how important the different coefficients are. So certainly there is a lot of weight which goes into the ground state. Then that's your first excited state. That's the contribution which each of these states make to the binding energy.
Okay. Thank you.
Of course, you see, as you go from the bare to the renormalized interaction, you also see that the mode entanglement sort of distributes itself in an ad hoc manner between the lower modes, but certainly not to the higher modes. Okay, the higher modes, anyhow, their contribution is suppressed. So this was, there was no dynamics here. So here this was just to illustrate, or rather make a connection between mode entanglement and the results you see here between these effective interaction and the bare interaction. That's all. And the fact that for this effective interaction you need fewer qubits or resources.
Okay. Thank you.
Any other questions?
I have a question.
Yes, please.
Sunethra.
Yeah.
In nuclear physics, we built up the correlation through Jastrow factor, which is somewhat like putting additional repulsive 1 over R square kind of interaction. Like for example, in Hall effect or in Calogero model, you can see Jastrow factor arises from 1 over R square kind of interaction. So when you looked at this effective theory, did you sort of get like 1 by R square kind of interaction, or what was it?
So for example, okay, that's a good point. So in all these things, the Jastrow correlations come because, you have wave function which has a wound and so on, right? So you have some part excluded. So you see, even if I had to start with a trial wave function with a bare interaction, you have to include this Jastrow correlation, this factor. And as a result, even the trial wave function guess becomes very complicated. However, with the effective interaction, you don't need that because there is no more wound anymore. Because these are soft interactions. Soft in the sense the repulsive pieces are traded to make it more attractive. So therefore, that is the reason that you can start with a simple starting point. And in fact, this was done way back in 2005, where there were variational calculation of the deuteron that was done for the bare and the renormalized. So a bare interaction needed a much more complicated variational start, whereas this renormalized interaction, a simple ansatz would work.
Very fascinating. Very nice.
Yeah.
So I also guess that with renormalized interaction, you would probably also be able to reproduce the other characteristics of deuteron nucleus, like magnetic moment and quadrupole moment, just like the binding energy.
No, that's that's a good point. So so yes and no. So whenever I have to compute, so any of these quantities you say are going to be observables. So therefore, as an expectation value, when I do a unitary transformation, here I've done unitary transformation on the Hamiltonian alone. Correct?
Yeah.
So therefore, its eigenvalues are preserved. So if it is some other operator, I have to do an operator running technically in order to preserve that value with the experimental number. However, it turns out that some observables, are only sensitive to the long range part. So even if I do not properly do an operator running, I can use the renormalized wave function and calculate an expectation value. And if the expectation value does not depend on the renormalization scale, I know that it was not so important to renormalize the operator because it was only sensitive to the long range part. So there is some separation of long and short range that one can see, but technically the correct way is to renormalize the operator. So do this unitary transformation for the operator itself.
Yes. And when one does that, and if one gets this similar answer that with n equal to 3 or 4, we are getting saturation or the expected experimental value, then only we would say that we understand deuteron completely through the renormalized.
Yes, so in fact it has been done, and it has been for any quantity you can do an operator running and get whatever has been whatever is known experimentally. However, from a very practical point of view, when a many-body computation is done, the right way of doing a many-body computation is to do this similar kind of renormalization in the presence of the medium, which is very complicated. It is being carried out. It's in finite nuclei. It's complicated, but most of many-body physics, a large fraction of people who do many-body nuclear calculation, they use two-body interactions as input. So if you use two-body interaction as input for a many-body calculation, you will see that in a traditional sense, you will have model dependence. With these effective renormalized interaction, you will have dependence on the renormalization scale, which means it's not properly renormalized. But the extent of dependence on the renormalization scale tells you how much of the missing forces you need to add, how important the missing forces are. And there is a physics intuition which comes into what becomes relevant. For example, if I work with a system of neutrons, just pure neutrons, I know that a three-body interaction is much less important as compared to screening. So screening in the presence of other neutrons will be more important to consider compared to a three-body interaction because of Pauli exclusion principle. So you have a lot of physics input which dictates how you need to account for these missing pieces so that you get independence with respect to the renormalization scale. So you use it as a tool to build in corrections. So this is a more practical way of doing a many-body computation. Of course, there exists finite nuclei calculation where the entire renormalization is carried out in medium. So then you will get independence with respect to the renormalization scale.
Okay. Thank you. Thank you. Any other questions?
Hello, ma'am. I wanted to ask that you used UCC ansatz for your VQE.
Yeah.
Why did you choose that ansatz, or could you have chosen other ansatz like HV or anything other?
You can, yes, you can use other ansatz. For example, the UCC ansatz is very physics motivated ansatz, right? Because what it does is it allows for excitations from the ground to the excited state and all possible excitations. And here I have only one particle. That's all I can do. Now there are other ansatz which are called hardware efficient ansatz, where you just have strings of Pauli operators, Pauli matrices, and you sort of you have exponential of Pauli matrices multiplied by some parameter, and then you can do this thing of optimization. So that also you can use. You can work with any ansatz, but UCC is more meaningful because it has a nice physics input. That's all.
I mean, HVA is also inspired by the Hamiltonian of the system. So could HV use Hamiltonian variation ansatz, which are inspired when they are constructed using the Hamiltonian of the system. So they also mimic the physics of the system very well. So could they also be a good choice of ansatz in the process of variation quantum eigensolver?
Somehow the name of the ansatz I missed. Could you please say that again?
Hamiltonian variational ansatz, HVA.
I see. Okay. Yeah. So yes, you can use any ansatz because after all, at the end of the day, it's just a starting point, right? It's a variational calculation. What ansatz would work certainly is worth the study. And there are also other optimization that one can use to minimize, to be more efficient with the qubit-wise resource, which is something called energy sorting, which is done in quantum chemistry, where you have these pool of operators which are going to build your ansatz, and you can ask which operator contributes most to the energy eigenvalue problem. Okay, so then you order the operators and you don't use all of the operators but use only a subset. So there are many ways to improve this. There are so this is in some sense some kind of adapt VQE that it would come under.
Okay, So if there are no further questions, let us thank Professor Ramanan once again for her very interesting talk. Thank you, madam.
Thank you very much.